So like I said, if you still need a few more minutes on the test, again, please take as much time as you need to at the end of class here. Those at the other locations, you can just turn it into the ITV office at your location. Here in Rice Lake, this room is empty for the hour after class if you still need to work. And if any of you decide that we're going through stuff this hour that you need your test back to work on it, just let me know. So anyway, we're going to start our new section here. We're going to deal with algebra and measurement, kind of fitting together two topics to make a unit. To start out with algebra, we have to understand algebraic numbers. We looked a lot in the first week at our regular numbers, our whole numbers, and how they were structured. We talked about having something like 4 inches and how that had two parts. The count, which was the 4, telling us how many, and the name, which was the inches. And that carried through into all sorts of other types of numbers. We had 4/7, which was still, the 4 is an amount. We have 4 of something, and now instead of inches, we have sevenths, and they behave the same way. When we start to get into algebra, we have 4x, or n, or 4y, whatever letter we want to use, and that behaves exactly the same way. We have a count, we have 4 of something here, and we have a name. Instead of inches or sevenths, we now have x is our name. And those numbers are going to behave exactly the same way. 4x plus 9x is going to make 13x. Just like 4 inches plus 9 inches would be 13 inches. 7y plus 9z is going to be 7, 9 plus 9z. They have different names. Just like taking 7 feet plus 9 pounds couldn't be done because they have different names. 7y plus 9z cannot be done because they have different names. We can, however, run into things like this. So far, those can't be combined, but if we keep going, we'll see that even though there are different names here, there are some of them that are in common, and we can gather those together. So we have the 8a and the 3a, which can combine to make 11a. So 13b and 9b, which can make 22b. Perfect. We cannot combine that any further because a's and b's are different names and they cannot be combined with addition. So here, a little bit extra complication because we have the subtraction in there. When we're dealing with algebraic numbers, we can actually think of that as subtraction, or we can put it with the number that goes after. Remember, subtraction, if I had 5 minus 2, that subtraction goes with the number that comes after it. It's telling us to add the opposite of that number that follows. When we're dealing with algebraic numbers, that subtraction symbol also goes with the number after it. This is 7x, but this here would be thought of as a negative 3x. And we can combine those. 7 and negative 3 make 4x. Then we have negative 5y and positive 2y make negative 3y. Now it should be noted here, since that was a negative 3, this is a minus here. Up here, because that was a positive 22, we connect them with a plus. When we went to multiply, however, we saw that if we had 4x times 9x, just like any other multiplication, we combine the counts. What's 4 times 9? 36. But we also combine the names. X times x is x squared, just like inches times inches became inches squared. What do we have? 5x times 3z. 5 times 3 is 15. X times z is xz. Just like working with any of our units, feet times pounds became foot pounds, x times y, or x times z becomes xz. We can multiply pretty much anything when we're dealing with our algebraic numbers. So anyway, enough of dealing with the generic numbers. There are several. Let's look at this name here, the x and the y and the z and a's and b's or whatever, and talk about that for just a little bit. Those are called variables, and it's actually a generic term for several different uses of the symbols. What we were using here was just a generic variable. It stands for a generic number or generic item. Happens a lot, used for defining rules and stuff like that, like defining a plus b is equal to b plus a. They don't stand for a specific number. They don't have a specific value. They're representing a generic representation of any possible number that could be used there. Well, a second way those variables could be used is they could be used in a formula. Sometimes in algebra called an expression. Possible formula might be for like the area of a triangle. There's base times height over 2, or 1/2 base times height. In this case, they're still representing unknown numbers, but they're not just generic like they are up here. Here they are waiting for a value to be given to them. If we are drawing a triangle, and we're given the base is 8 inches and the height is 5 inches, now we can put those numbers in place of those letters, those variables, and we can find the area. Put in the 8 for the B, the 5 for H, multiply to get 20, which would be inches squared. So we're going to evaluate a formula. We're going to look at this a little bit when we start looking at temperature conversions, body mass index formulas, and stuff like that. Then the next way that it can be used is it can be used for an unknown but set value. For example, 3x minus 7 equals 17. In this case, it's still representing a missing number, but it cannot take on any value. Up here, B and H could take on any value depending on what triangle we drew, or almost a value. It couldn't be negative or 0 or any of those. But a large range of values. Here, this variable has exactly one value. We just don't know what it is yet, but we can figure out what it is. And that's actually going to be the next thing we cover, is looking at those types of variables and that usage of a variable. So let's look at those. Of course, they're called an equation. And all of our equations start out in this form, as a variable equals a number. And to understand how to work with equations, we have to understand the symbols here first. Most importantly is this symbol here, which is called the equal sign. Now, here's the hard part. We're so used to that equal sign and we use it so much. What does it mean? And don't say equals. But what it means is what's on one side of the symbol has exactly the same value as what's on the other side. In fact, we could think of it as a balanced scale, as what's on the left side will exactly balance what's on the right side. Now, as I said, all equations start out in this simplest form, as a variable equals a number, and they're built up from there. So we have to look at what types of things can be done to build onto an equation. We could add to the equation. We could add 7 to my variable x. So now this becomes x plus 7. But again, because of that balanced scale, if I add 7 to one side, the scale is going to tip, isn't it? So what do I have to do? I have to do the exact same thing to the other side. I have to add 7 to the other side to keep it balanced. So over here it is now x plus 7, but that now equals 13. 6 plus 7 is 13 instead of 6. So we just built onto that equation, made a slightly more complex equation. Now, if we are ever asked to solve an equation, what they're really asking us to do is to take this equation and take it back apart. Get it back to this form of a variable equals a number. Well, this equation was built by adding 7. How would we take it apart? Subtract 7. If we subtract 7, it takes that piece off and leaves us with just the variable x there again. But again, because of this whole idea of a balanced scale, whatever I do to one side, if I want to keep the scale balanced, I have to do the exact same thing to the other side. So I have to subtract 7 from the other side. 13 minus 7 is 6. So I get x equals 6. Now that's what we started with. That's what the equation began as. So we know we did that correctly. Now in this case, we built the equation here, so we knew exactly how to take it apart. The tricky part usually is figuring out how the equation was built. So let's take a look at how we would do that. So let's look at something like this. 5 is equal to y minus 9. To figure out how an equation is built, you find the equal sign, then identify which side has the variable. In this case, it's on the right side. Then on that side of the equation, you ask yourself, what is keeping my variable from being alone? Right now it is the 9. So next you'd ask, what operation is attaching that 9 to the variable? Subtraction. So this equation was built by subtracting 9 from the y. How would we take it apart? Add 9. Makes that 9 go away, leaves us with just y over there. But remembering to do the exact same thing to the other side to keep it balanced. So 5 plus 9 is 14. So y equals 14. Now if we get to this point and we're not sure of ourselves, we can always go back to this original equation and we can replace the variable with the 14. Is 5 equal to 14 minus 9? You bet it is. So that must be the correct answer. We might have something like this. Looking at this, again, we find the equal sign where the variable is. What's keeping my variable from being alone? Multiplied by 13. Good. So to take it apart, we're going to divide by 13. It's gone, leaving us with 7. We have to do exactly the same thing to the other side. 52 divided by 13 is 4. We could double check. 13 times 4 is 52. So it works. Those are pretty simple equations. They get more complex. And once they get more complex, the difficulty is figuring out how they were built. We might have this equation again. 3x minus 7 equals 17. Go through the same process. Here's the equal sign. Here's where my variable is. On that side of the equation, what's keeping x from being alone? 3 and 7. What operation is attaching the 3? Multiplication, and the 7? Subtraction. Now, according to our order of operations that we looked at a couple weeks ago, what do we do first? Would we subtract first or multiply first? You multiply first. So when this equation was built, what was done to the variable was it was first multiplied by 3. X was multiplied by 3. Then the 7 was subtracted from it. Now, you put anything together, whether you put together a piece of furniture or a toy or a model or whatever, and you've just finished, you've just put on that last piece, and you go to take it apart, what's going to be the first piece you take off? The last piece you put on. Same thing goes for these equations. When we go to take it apart, the first piece we're going to take off is the last piece put on, the negative 7. No, subtracting 7. So how do we take that off? Adding 7. That's gone. We have 3x here. We have to add 7 to the other side to keep it balanced. 17 and 7 makes 24. Next, we have to get rid of the multiplying by 3 by dividing by 3. Good. X equals 8. Once again, if you're unsure, you go back to the original equation. I can replace x with 8. So 3 times x becomes 3 times 8 minus 7. 3 times 8 is 24. Minus 7 is 17. Have you guys try that one in your notes quick. See what you come up with. So if we look at this one was built, and I don't expect you to write this out, but what's been done to my variable y, it's been multiplied by 5, and 3's been added to it. So to take it apart, we're going to subtract the 3. So 45 equals 5y, and then divide by 5. 9 equals y. And again, you could put 9 back in where the y is. 5 times 9 is 45, plus 3 is 48. So let's check out. Well, if you haven't learned by now, I always make it worse. What's different in this one? There's a parentheses. Whenever we see a parentheses, it should scream at us. Do something here first. So the first thing we always have to check, is there anything that needs to be done inside those parentheses? No, 4x minus 3, I cannot combine those. This is an x and this is just 3 ones. Can't combine them. Second question is there anything that needs to be done to the parentheses? And in this case there is. It is multiplied by 5. So we're going to do 5. We're going to distribute it through, for those of you that know that. Otherwise, if you haven't learned distributing, technically what's going on there, just 4x minus 3 times 5, just like any long multiplication. 5 times negative 3 is negative 15. 5 times 4x is 20x. But for our purposes, we're just going to use the shortcut of distributing. 5 times 4x is 20x. 5 times negative 3 is negative 15, and that equals 45. So from there to solve, what do we have to do? Add 15. 20x equals 60, and then divide by 20. Perfect. X equals 3. We could run into something like this. What's different here? Yeah, we find our equal sign and we go to identify where the variable is. The x appears twice. Fortunately for us in this case, both of them are on the same side of the equal sign, which means, if we're still thinking of that balanced scale, I can just push them together into one big pile and the scale's going to stay balanced. It's not going to change my balance of my equation. So I'm going to take 7x and 2x make 9x. Now I still have the positive 4, the plus 4. It still equals 40. From here, of course, we should be getting pretty good at this. What do we need to do? Subtract 4. 9x equals 36. And then divide by 9. X equals 4. And again, you could go back up here and put 4 in where you see the x's. 7 times 4 is 28, plus 4. 2 times 4 is 8. If you add those all up, you do get 40. I'm not going to do that. Oops, go ahead. So I heard someone speaking up. I'm not going to do this double check anymore. I'm going to assume you guys can do that on your own. But remember, you can, in every problem, you can always put the answer back in for x and double check it. What's different on this one? The variable appears twice, but this time it's on each side. I cannot just push them together anymore because they're not on the same side of the equation. They're not on the same side of the scale. So what I have to do here is get rid of one of them. And normally I'll get rid of the smaller one of the two, in this case, the 2x. And getting rid of it, literally I'm just grabbing it and pulling it off and throwing it away. Mathematically, that is taking it away, subtracting it. I take away 2x and I'm left with 45. But this is still a balanced scale. If I take 2x off of one side, the thing's going to tip. So I have to make sure I take 2x from the other side. The only place I can take 2x from is the 7x. 7x minus 2x is 5x plus 5. And then subtract 5. 5x equals 40. And then divide by 5. X equals 8. Again, you can double check it, but we're not going to bother right now. Well, since you guys seem to be okay with equations, I'm going to let you guys try one here. Try that one. See what you come up with. We'll talk about it in a minute. Just a little bit more complicated. Okay, let's see how you did. Now, when we have an equation as complex as this one, we can actually take the equal sign and work with each side separately. So I'm going to work on the left side first. Over there, I see parentheses, which should always draw my attention and tell me to start there first. So in the parentheses, is there anything to do? No. Is there anything to do to the parentheses? Yes, there is. Times 3. So 3 times 7x, 21x. 3 times negative 2, negative 6. And then we still have the plus 7 there. Now, before we go over to the right side, I'm going to combine what I can. So 21x is going to stand alone, but negative 6 and positive 7 make positive 1. Over here, I have parentheses. Anything to do in them? No. To them? Yeah, times the 4. 4 times 2x? 8x. 4 times 1? 4. We still have the positive 12x and the positive 1. Now, of course, we're going to combine again. 8x and 12x make 20x. 4 and 1 make 5. Now if we simplified and reduced everything we can on each side of the equation, now we can start looking at the equation as a whole. What do we do next? Perfect. We see that there is a variable, the x is on each side of the equation, so we have to get rid of it on one side. 20 is the smaller one, so I'm going to take away 20x. It's gone. Leaves me with 5. Have to take 20x from the other side. Can only take it from the other x's. 21 minus 20 is 1x. We still have the positive 1. Now 1x can actually be thought of as just x. Just like 1 inch is sometimes just called an inch, we can think of 1x as just an x. So to solve, all we have to do is subtract 1 and x equals 4. How many of you had x equals 4? Is there anybody that really doesn't know how we got there and wants to see another example? Everybody figured it out after we did it? Okay. Well, our next step, I know we only have 11 minutes left, but want to get started on it. We will go over this again next week, I promise. But our next step is to start talking a little bit about mixture problems, solution problems. And to first get into that, we have to talk a little bit of background science on solutions. Solutions have two parts. They have a solvent and they have a solute. The solvent is the base substance, the larger substance. And in a solution, it's called a solution because one substance dissolves. The solute is the substance that dissolves into the solvent. What happens, if we're looking at it scientifically, the solvent has particles. Sometimes it's water, sometimes it's alcohol, sometimes it's air. The solvent can be liquid, gas, or even a solid in certain cases. The particles have space between them. The solute then usually has smaller particles, and it fits in the gaps between the particles of the solvent. And it fits in those gaps and it stays there, it locks in. Being dissolved means I can let, like salt water, if I properly concentrated salt water, if you don't put too much salt in it, you can leave it sit on the table forever and that salt will stay in it. It will never fall to the bottom. Now, if you put cornstarch in there, however, cornstarch does not dissolve in water. You can stir it up and it looks like it's dissolved, but if you let it sit there long enough, it'll eventually settle to the bottom. That's not a solution. So anyway, the concentration of a solution is usually given as a percent. Let's say we have a 12% concentration. What that means is 12% of the total volume is the solute. So if I want to find the amount of solute in a solution, it is the total volume times that percent is a rate. So if this was 12%, still it'd be times 0.12. So whatever the volume of the solution times 0.12 would give us the amount of the solute. When we are mixing two solutions, it is the amount of the solute that matters. The first amount plus the second amount, the amount of solute in the second solution, will add up to the total amount of solute. So let's say that we are mixing 300 milliliters of, let's go 18% solution. Doesn't really matter what's being dissolved. And we're going to mix it with 500 milliliters of, what do I put in here? 26% solution. You want to find the concentration of the resultant mixture. Well, again, we're looking at the amount of solute in the first solution plus the amount of solute in the second solution has to equal the total amount of solute. So whatever this is being dissolved here, the first one has 300 milliliters times 18%. Now normally what I would do is I would do this. 300 times 0.18, like that. That is the amount of solute in the first solution. Plus the amount of solute in the second solution is 26%, so 0.26 times 500 milliliters. Now my total amount, I don't know the concentration, so that's going to be X, times, do I know the volume? Yeah, 300 plus 500 means 800 milliliters. Has to be the volume. So we do 0.18 times 300 is 54, correct? Plus 0.26 times 500 is 130. Because X times 800. I'm going to combine 54 and 130 is 184. And I'm going to solve this by dividing by 800 to get x by itself. If I divide that by 800, I get 0.23, correct? Equals x. So what that means is the concentration of this resulting solution is 23%. Make sense? Okay. So then, what if I ask it in a slightly different way? Let's say I ask, say we need 61% solution. I want to know how much 54% solution to mix or combine with 400 milliliters of 75% solution to get the 61%. So we're going to combine 54% with 75% to get 61%. We have amounts here. We have 400 milliliters for the 75%. We're asking how much of the 54%. So I'm going to let that amount be x. How much of the 61% are we going to have? X plus 400. This amount plus this amount. Just like up here, it was 300 plus 500 gives 800. Same down here, only we don't know one number. So it's x times 400 gives us x plus 400. So now we'll write out our equation. This is going to be 54%, so 0.54 times x plus 75%, 0.75 times 400 equals 61%, 0.61 times x plus 400. So this is just 0.54x yet. 0.75 times 400 is 300. 0.61, we're going to multiply through the parentheses, that's 0.61x. 0.61 times 400 is 244. Now what? We'll get rid of one of the x's. We'll get rid of the 0.54x because it's the smallest. So 300 equals 0.07x plus 244. And then subtract 244. .07x equals 56. And then divide by 0.07 to get x by itself. X is 800. I know it's milliliters because up here it was milliliters. So that means we have 800 milliliters of the 54% solution mixed with the 400 milliliters of the 75% solution. What do y'all think? Better than a sharp stick in the eye? Maybe? Not sure? Okay. Well, for next week, we didn't get through everything on the list, so it's only going to be page 49 through 50. 1 through 43, the odds. Those are the ones you should definitely try to have done. The next set here, page 53 through 54, 1 through 15. I would try them, but we just started on those mixture problems, so I'm not expecting you to be perfect at them. We will spend more time next week on those. And I just lost the network. You guys have a great weekend.